Greetings and welcome to my final year project demo titled Deep Learning for Computer Chess. I'm Rohan Kapur and I performed this project under the esteemed supervision of Prof. Herring. Before we move on to the details of the project, let's take a look at the motivation behind this. So the modern problem of chess and AI stems from the fact that there are 10 raised to the power of 50 positions that exist on a chessboard, and even if each of these positions was evaluated every thousandth millionth of a second, it would still take us the amount of time that you see on your screen to evaluate all the possible positions. Hence, we need computers to come in and help us. A brief background. There have been many strides in the advancements of AI and chess, with IBM's Deep Blue to Google's AlphaZero, which remains unbeaten currently by man or machine. However, there are several limitations that exist of traditional models, such as machine learning having hard-coded features, or the fact that they use brute force instead of pattern identification. We therefore employ deep learning. Deep learning is the use of artificial neurons or neural networks, which are very similar to the way in which the brain functions. We identify important features on our chessboard, such as the side to move, the number of pieces remaining, how many pieces does white have, whether or not black can castle, amongst many other features, and assign importance to them. We evaluate the winning odds of every position by looking at this aggregation of features over a very large data set. Hence, the objectives of this project were set out to be threefold. First was to explore, to train the giraffe and deep chess deep learning based models and get the best possible accuracy on a large enough data set. Second was to enhance. We implemented the Monte Carlo tree search after the positions have been evaluated with the evaluation function as early termination instead of going all the way with our MCTS. And lastly was to evaluate, to play a 100-game chess match from our engine against a traditional engine, just like the authors of Google's AlphaZero did when they first came out with AlphaZero. Let's take a look at the first part, which was training our deep learning models. The first model we looked at was Giraffe. Here we used a dataset of 10,000 Grandmaster games from which we generated more than 370 features. We labeled each of these features using the Stockfish engine and then designed our model architecture, which is basically a neural network. As you can see, this is what the architecture of Giraffe looks like, where the input is divided into three sets of features: the global features, piece-centered features, and the square-centric features, each of which is fed as a separate input into the first hidden layer, which are then combined and sent into the second hidden layer. We performed a variety of experiments on this, considering regularization by adding dropout layers, connecting all of the inputs, as well as using different loss functions such as mean squared error, as well as binary cross entropy loss. Finally, this was one of the best results that we got in terms of the accuracy and the loss for the training and testing data set, as you can see on these curves plotted by the number of epochs. The second model we looked at was the superior deep chess. Here we extracted our data and represented each chess board as a bit board, which basically consisted of 773 bits. So instead of having a table with a number of features, we were able to represent each position as a vector. We fed this into auto-encoders, which were able to evaluate these positions and learn from the evaluations that they had made previously. And finally, we created a deep belief network, which basically consists of a Siamese disjoint network that had two separate deep belief networks connected to the main architecture to form the overall deep chess architecture. The training results are much smoother than Giraffe, as you can see on the screen, because this happens to be the far superior architecture as well as trained on a larger data set for a longer time. The model summary for both the models is as follows. We got the best accuracy on the testing data for Giraffe to be 84%, whereas for deep chess it was a whopping 98%. And the loss for Giraffe was brought down in the end to 0.03, whereas for deep chess it was brought down to just 0.01. The second part of this project was implementing a Monte Carlo tree search with the early playout termination using our deep chess function as early termination function. The basic idea behind Monte Carlo tree search is that it has four main steps. The first is the selection, where the algorithm starts at the root node of the search tree and then selects the child node with the highest value of a score called the upper confidence bound, which is a measure of how promising this node is. This value is calculated using a formula that balances the exploitation of nodes with high win rate, as well as the exploration of nodes that haven't been visited as often. Once the algorithm reaches a leaf node, which represents a state of the game that hasn't been explored yet, it expands the tree by generating all possible legal moves from that node and adding corresponding child nodes to the tree accordingly. We then move on to the simulation step, where the algorithm randomly simulates a game from the newly added child node until we get a result. And this is done by playing moves from both sides until the end of the game is reached based on a random strategy or a predefined heuristic. And the last step is back propagation, where the result of the simulation is back propagated up the tree, and you can see the number of wins by the number of nodes that are visited are updated for each and every node. So where we come in with the early termination idea is in the simulation step, so that we can provide that for a certain depth. We just stop the simulation there, so we don't have to simulate the entire tree, but instead use our deep chess evaluation function to make the search a lot faster. On your right, you can see how we've implemented this via class diagrams in Python. We also performed certain experiments to see at what depth do we get the best score and at what depth do we get the optimum speed for our engine itself. Obviously, for the time parameter, as the time increases with the depth, but for score, we found that it was optimal to use a depth parameter of 3 so that we were able to obtain the best efficiency. We evaluated this against another engine that basically did not use Monte Carlo tree search to be able to find out what the best performance was. Let's move on to the third part, which was to evaluate using the chess matches. Let's take a look at a quick demo of our deep chess engine played against a traditional engine called Olive Chess. Here we are at our demo screen. As you can see, here we load our deep chess engine from our deep chess engine Python file, and we use the Olive chess engine as the enemy engine to play against. Using some simple code that decides to play a game, we are able to try and make sure that we can simulate a game for both of these engines. So let's start the game and see what it looks like. You can see that we are able to present the number of moves made, the side to play, as well as the last move played and the moves made so far. As soon as our engine makes the first move, there we go. So you can see that our engine is white and the enemy engine is playing in black. And the enemy engine is very quick in making their moves, but since our engine has to evaluate using the model that we have trained locally, our engine takes time to go through each of the evaluation functions. However, we set a time limit. But for us, it's more about accuracy as well, not just speed. Therefore, we think that this is a good metric for evaluation. You can see that the moves made so far is being updated here, so you can follow the entire game as it's going on. You can also see what the last move played was, and accordingly, the game goes on. Let's fast forward through this game that we can see what the result of deep chess versus Olive chess is like. Alright, wow, as you can see, deep chess, which is playing on white, has won this game. That's a very exciting result for us, and you can see the entire move log here as well. Feel free to try and go over this game again as well. We played this match many times before ourselves. While the demo was for the interest of the viewer and played just one game, for our experimentation, we played a 100-game chess match of deep chess versus a traditional engine like Olive chess. And we found that 41% of the time, deep chess was able to take it, whereas Olive chess took it away 53% of the time. So out of 100 games, deep chess won 41, lost 53, and there were 6 games that were drawn. You can see these statistics to find out that the number of move distribution for these 100 games seem to be ranging from a very low number of moves to some games even having about 340 moves, and these games probably ended in a draw. And the average stockfish evaluation per game shows you that this was not really necessarily a one-sided affair, because even though the white and black were switched every single game, so that deep chess was white in one game and black in the next game, you don't see a clear inverse fluctuation to show you dominance from any side in particular. So the overall score was 43 to 51. Similarly, we did a 50-game chess match between deep chess and deep chess that implemented the Monte Carlo tree search with early playout termination. And we found that the Monte Carlo tree search with a depth of 3 was far superior to deep chess and beat deep chess every single time. This was a modified version. So the MCTS EPT beat out the alpha-beta pruning-based deep chess engine every game that it played against it. But deep chess did put up a fight, as you can see in the average evaluation, as well as in the number of moves distribution. Therefore, we concluded that Monte Carlo tree search was better than alpha-beta pruning when it came to our own model. In terms of the future work, we'd like to train the model on a larger data set, implement the MCTS solver, as well as create a bot account on Lichess and get an engine rating for our engine in particular. Thank you so much, and hope you enjoyed looking at our demo today.